continuing our theme of cute animals. I wonder what I'll do next unit. I really like this one. I think he's cute.
Name him Bob.
I think we can do better than Bob for this guy. I don't know why.
Bobby.
No.
Orlando Jr.
Juan Pablo? We have a winner. Okay, I like that. Okay, so next we're going to look at the other thing we can do. Yesterday when we looked, or 2 days ago, when we looked at doing translations, what were we always doing? We could move it up, which we did by adding to the y values, or you can move down, which we did by subtracting. You can move it left, which we did by adding to the, and we can move it right, which we actually did by subtracting from the x values, right? But what operations were we doing? Adding and subtracting, right? And when you add and subtract, you change all the values, but you change all the values by the same amount, right? So every y value, if you subtract 8, every y value gets lowered by 8. So the whole thing just moves down. And if you add 3 to the x, then everything moves to the left by 3, right? But everything moves together. And we call that translations, right? And one of the things that happens then is that the basic shape of your function, did it change? No, it moved, shifted. It's the equivalent of, when you paste an image in, if you just grab it and move it around. And literally, what a computer is doing in that case is it's moving every pixel, its x and its y value. Every pixel on your screen has an x and a y value. When you move an image around, it's just changing the x and y values of every pixel in that image so that they're in a different place on the screen. Does that make sense? But what's another operation we can do? We could square root. We're going to think of that as a function, not a translation. So that's one of our parent functions, actually. Same with squaring. That's one of our parent functions, right? That makes a parabola. You could think of that as a translation, but we're not going to. We're going to think of it as a function. Multiplying and dividing. When you multiply numbers, how is that different than adding? Yeah. See, when you multiply, multiplying is just like adding, only you're adding by different amounts each time, right? If you multiply every number in a set by 3, well, 0 doesn't change at all. It stays 0. 1 will change by 3, but 2 will change by 6. And 3 will change by 9, and 4 will change by 12, and so on and so forth. Does that make sense? So when you multiply, the change that happens depends on the value of the number. That's not true with adding and subtracting. You add 5, every number changes by 5. But you multiply by 5, every single number changes by a different amount. What's that look like on a graph? Well, let's take a look. So here, let's do the same thing we did last time. Let's start with our base parabola. And I don't even need to show the math now because it's all listed here anyway. If x is negative 2, what's? Oh my, well that's very... Shame on you, Joe. If negative 2 is our x value, what's x squared? And negative 1 would give us, and 0 would give us, and 1 would give us 1, and 2 would give us 4. Okay, we get that typical parabola here. Now, let's change this such that we use all the same x values. But now let's multiply it by 2. We could write that as 2x squared. Nothing wrong with that. We could also say that that's the equivalent of just taking our original function and multiplying it by 2. But notably, either way we look at it, are we changing x values or y values here? And how do we know that? Yeah, it's outside of the function. Order of operations would say first we do exponents, then we multiply. So we have already made it a parabola before we multiply it by 2. In other words, we're not changing the input, we're changing the output. So the x values stay the same, but the y values, 4 is going to become 8. 1 is going to become 0 is going to become
0.
1 will 2, and 2 will become
8.
Awesome. So now, what's that look like on a graph? Well, 0 still lives at 0. It hasn't changed, but this 1 value, where did it go to? It went up to 2. And I'm going to actually draw a little arrow to show that that's the point that's moved. What about this 4? Where does it live now?
8.
Way up at 8. What about this 4? Way up at 8. The result of that is a parabola that looks like what? Yeah. So one way to think of this, absolutely, is as having changed the step pattern. So if we think of this as being the a value of the parabola, we've changed the step pattern. But the other way to think of it is this. Okay, ready? Need my keyboard here. I don't have my lectern. I don't know how people teach without a lectern. I need a lectern. So, if we have x squared, there's our original parabola, right? The other thing I could have done is if I took this and pasted it as an image. Does it let me do that? It doesn't. There's a way. Let me take a look here. So if I took this, here it is. How could I stretch this by 2? Well, this is, one sec. This would be translating, right? Move it left, move it right, move it up, move it down. That's all just adding and subtracting x and y values, right? But what would stretching it look like in this equivalent? Yeah. Yeah, and having it go twice as long, right? Which here I'm just going to have to estimate, but say like that, right? That would be applying a stretch. Do we see that? And what it looks like in practice is that it gets kind of longer and skinnier, right? I'm going to see if I can do something here. We'll just save it to desktop, and we'll call it parabola. And we'll go to desktop, and we'll find parabola. I know this is all a little stupid, but I just want to kind of demonstrate this. Desmos will take images. And so if I took this image in Desmos, and I'm going to get rid of the grid back here. I'm going to get rid of the axis numbers. Okay, so here's my image in Desmos. If I make a second copy of it, which I think I can do, whoa. What would the equivalent here be? Would I want to change the width or the height if I wanted to show this being stretched? Well, what did we change here? The x's or the y's? Oh, for God's sakes. We changed the y's. And how did we change them? We made them all taller. How much taller? 2 times taller, right? And what would the height be if we made it 2 times taller? 20. And what do you notice? It looks like that, right? Which, if we put our x squared graph on here, do you see how that fits perfectly? I mean, pretty perfectly, considering it's just a picture. And how will this one fit? Well, not as well, right? Now, what function could I put on there to see if we nailed it? 2x squared, right? And again, it's just an image, so it's not perfect, but it's pretty darn close, yeah? Does that make sense? By taking the image and making it twice as tall, we make that function, which makes sense because what have we done to all the y's? Multiplied them by 2. All right, I want you to take this one, and instead of stretching it, right, what we call it when we multiply it by a number that makes it bigger is we call it stretching, because we're taking all the y values and making them bigger. What would we call it if we took all the y values and made them smaller? Yeah. Now, you could do that by subtracting, but that wouldn't be compression. That would be translating it down. So we have to not subtract, we have to divide. And here, we're going to multiply it by a half, which is the same as doing what? What are we really doing when we multiply it by a half? Well, we're multiplying it by numerator times numerator. You're multiplying it by 1. Does that change it? But then what does this symbol mean? Dividing. And so you're dividing by 2. So multiplying by a half is the exact same thing as dividing by 2. Now, you know that with a half, we're pretty comfortable with that, right? But when you get to more complex fractions, never forget a fraction just means dividing. Does that make sense? Okay, so do that. I copied and pasted the previous one, and I did the exact same nonsense of this M. I got all confused. I'm so sorry. We'll just call them F and G again. I'm so sorry. I'm a failure. I failed you. I'm embarrassed. I'm ashamed. I should have thought to change this one too, because obviously it was also the same as the previous, but I didn't. So take a minute and do that. You should be able to fill this out. I guess we can fill the base function out. You can do it yourselves. Fill this out, and when you think you got it, somebody come put it here. I'll be back in 2 minutes. I'm going to check on my room and glare at kids who look like they're not being neat.
Oh yeah, by the way, I was just putting the wrong numbers. No more questions.
Oh, you got it figured out?
Yeah.
Good for you. That's awesome. Hello.
So what is this supposed to mean? Man, I'm working on my assignment. I'm not doing this.
Guys, I'm doing it. That's all just the bunch of stuff. But what was the X here? Actually, no, I'm just going to You're not helping. I'm just kidding. Also, just divide this. Oh my. Why didn't you tell me that earlier?
He said that 3 times. I said that 4 times. You couldn't even. Okay, so you know what he was confused about?
Now we didn't sit on the board. Nobody put on the board. What's wrong with you people? That's okay. How we doing? What do we got?
I don't know, because it's all blank here. I don't know what to put.
Yeah, what'd you get? Parent function, talk to me. What's it look like? Okay, yeah, 0. We take the square root of 0. We get 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. And square root of 16 is 4. Those are obviously carefully chosen numbers, right? Cool. Okay, then what's this going to look like? Okay, now we said to take half. Why aren't these 0.5, 2, 4.5, and 8? We're not changing the input. We're changing the output. How do you know that? That's right. If you look here, what we're saying is we can multiply the output by half, which would give us 1/2 x. If you want to do 0.5x, you could, or 1/2 f of x. So that would be 1/2 f of x, or 1/2 root x. Doesn't make a difference, which in this case would be 0. This case, 0.5, or if you prefer, a half. Here, I shouldn't put a bracket. That means multiply. Here, 2. Oh, sorry, 1. Here, 1.5, or if you prefer, 3/2. And then 2. Okay, so let's graph this on. That would be 1. That'd be that. That'd be not. Yep, there's 9, and that needs to be at 1, 2, or 1.5, right? That would be 1.5 there. Cool. And there's our modified function. And sure enough, what's it look like? You multiply everything by half. Lo and behold, it's the same shape, only it's been squished down, so it's half as tall. And we call that squishing compression. All right.
I have a quick question.
Yep.
Do you have, like, because I'm trying to find the common denominator, but because there's, like, none of them match with each other, do I just put all of them as the common denominator?
Yep. But I want you to focus on this right now, okay? Okay. So, what about if we do want to do a horizontal stretch or compression? This is not something you've ever actually done to a parabola before. In our parabolas, we always did our stretching or compressing with the a value. Was the a value ever in the bracket on purpose? Sometimes when we did some weird factoring, it got in there, right? But generally speaking, we like to keep our a value outside because we like to do consistent stretching and compressing of the y's. But could we stretch and compress along the x's? Now, what do we know about our x's? They lie to us, right? Which means, let's look at this example. Let's do the original function, x squared, so that gives us 4, 1, 0, 1, 4, right? And now let's do f equals 1/3 x. In other words, first divide the x's by 3 and then square them. Now, pens down. Everyone's pens down. Ready? You promise? Okay. If I didn't write this, could I divide all these x values by 3? That's what this tells me to do, right? I could do that. I could say -2/3, -1/3. Again, don't do this. Pens down. 0, 1/3, and 2/3. Nothing wrong with that. And then could I square them? Because that's what we're doing here, right? And that would be 4/9, right? And this would be 1/9, and that'd be 0, and that'd be 4/9, or 1/9, sorry, and then 4/9 again, right? The problem with that is I've now changed the x's and the y's. Nothing wrong with that, but it means that it's hard to follow how this has changed. Does that make sense? Instead, let's imagine that to get this 4, what did I have to do? Well, I had to take -2 and I had to square it. But now, we're dividing all of the x's by 3 first. So if I want to square -2, right? Because that's what I did here. I said, okay, we're going to take -2 and we're going to square it, and that equals 4, right? The problem is, at the beginning, I've divided by 3, right? That's what we've been told we have to do. What x value is going to have to go up here if I want it to end up being -2 squared to give me 4? Almost 6. -6. Does that make sense? If we throw a -6 in here, then when we actually do the function we've been told to do, which is to take the x and divide it by 3, which I could write as x over 3. Right now I'm going to do it as 1/3 x, though that's the same thing as x over 3 squared. They mean the same thing. Do you see how that ends up giving us the same y value? And since what we're changing is the x, why not figure out what new x value would give me the same y value? Does that make sense? Well, we'll talk. Let's take a look. So then, what about here? What did I square to get 1? Yeah, -1, right, in this case? Okay, but again, we know that our function is we're dividing by 3, right? So what x value would I have had to put up here to get that -1 to square it to get 1? -3. So if the old x value is -1, what's the new x value have to be? It has to be -3. And then this one doesn't matter, right? Because what did I have to do? 0, I had to square it, right? Well, what could I have put in here? Well, it really doesn't matter, right? Because whatever I divide by 3, there's only one number that would work, which is 0. So this is still going to live at 0. That x value didn't change. And then we could do it again. Here I did 1 and squared it and got 1. So what did I have to divide by 3 to get 1? 3, right? So if I put a 3 in, 3 divided by 3 is 1, and then I square it, right? That gives me 1. And finally, what value did I have to put in here? I want it to equal 2 squared, which is 4. But if I'm dividing by 3, what do I have to put up here? 6. So what was the original x value I had to put in? 6. Okay, so look. When we apply a change to the x, if I want to keep the y values all the same, I have to change the x's. But if the x is being divided by 3, what did I have to do to all my x's to keep it the same? I didn't divide them by 3, I multiplied them by 3. Because by making the x values 3 times bigger, once we divide it by 3, it behaves like the old x value of -2. Does that make sense? So -6 will behave like -2 did. And -3 will behave like -1 did. 0 will still behave like 0 did. 3 will behave like 1 used to. And 6 will behave like 2 used to. Yeah. Well, that's the function. What we're doing here is we're taking x divided by 3 or 1/3 x. Does that make sense? And what we're saying is that if we wanted to get these same y values, because we know what are we changing here? We're not changing the y's, we're changing the x's. So to leave the y's the same, because we're not changing the y's, we're changing the x's, how do the x's have to change? And the answer is, if the function says to divide all your x's by 3, then when you actually work out what the x values are, they're not divided by 3, they're actually multiplied by 3. Because what do our x's do to us? They lie. They do the opposite of what we expect. Does that make sense? If the function says divide your x's by 3, what it's saying isn't take all the x values you had and divide them by 3. Rather, it's saying all of the new x values will have to be divided by 3 to behave like the old ones did. Which means all your new x values don't have to be divided by 3. They actually have to be multiplied by 3. And again, if that's too confusing, just remember x's lie. Whatever the function says to do, we actually do the opposite. Does that make sense? If the function says divide your x's by 3, to actually find the new x's, we don't divide by 3, we multiply by 3, right? Because multiplication is the opposite of division. And if you want to track this, 0 stays right where it is. But this got multiplied by 3, so 1 is going to end up way out at 3. And this one's going to end out at -3. And then this one's going to go all the way out from 2 to 3, 4, 5, 6. Does that make sense? These get stretched out. Oh, I totally took that to 4, didn't I? Whoops. 2, 3. There we are. Did I take that to 6? 1, 2, 3, 4, 5, 6. So I got 1 right at least. That's a miracle. 1, 2, 3. And 1, 2, 3, 4, 5, 6. Right, so we multiplied by 3, we multiplied by 3, multiplied by 3, multiplied by 3. You don't have to show all that, but the important thing is, what's the new function look like? When we divide the x's, you'd expect them to get smaller, but all the x's actually get bigger. So what does our function actually look like? It gets stretched. So when we change the x's, dividing doesn't compress it. Dividing actually stretches it, the opposite of what we'd expect. Which, if dividing stretches it, how would you compress it? Multiplying, right? So we would say that this is stretched by a factor of 3. And then if we wanted to, with this one, we could compress it by a factor of 2, which means we have to take it and multiply it by 2, right? Now what I want you to do, let's do the main function here together. If the original function, oh, for God's sakes, this is the worst note anyone's ever made. Actually, this is so humiliating. I'm ashamed of myself. Guys, I'm giving everyone 5 bonus marks on tomorrow's quiz for what a useless note this is. Actually, can you remind me of that tomorrow? I will forget. Okay. This is 1 over x. I'm sorry about that. So, what's this one then? 1 over -4 would be negative 0. 1 over -4? 0 point. Very good. 1 over -2 would be negative 0 point. 1 over -1 would be -1. 1 over 1 would be 1 over 2 would be 0.5. And 1 over 4 would be 0.25. Good. Do we see those points here? Yep. Let's put that original one on. Oh God. Okay, guys, I'm fired. Can we talk about that? I'm fired. Guys, listen, look at me. Do you know what I am right now? No, I'm ashamed. That's what I am. We discussed this. What am I? Ashamed. Okay. What I did was change this when I didn't mean to change that. I just meant to change this. So I'm silly. So let's try this again. This isn't 1 over x. It's 2 over x. Let's try this again. What's 2 over -4? Negative 0.5. What's 2 over -2? -1. What's 2 over -1? -2. What's 2 over 1? What's 2 over 2? What's 2 over 4? 0.5. There we go. Hey, that's the graph we have here. Okay. Look at me. Do you know what I am? Embarrassed. I am. I'm abashed. I'm very embarrassed. This is embarrassing for me. I'm feeling very guilty. But what I want you to do is compress it. But I want you to compress it horizontally, and I want you also to reflect this one. We're going to do 2 things. Look here. We're going to reflect it, and we're going to compress it. What does it mean to reflect something? Flip it. All right? You look in a mirror and you raise your right hand. What hand is being raised by your mirrored friend? It's left hand, right? It's a mirror opposite of yours. How do we mirror this? If we mirrored it, it would mean that everything that right now is on the left would be on the right, and everything that was on the right would have to move on to the left. So how do you do that? by multiplying everything by a negative sign. So all the x's that were positive, we're going to have to make negative. Okay, so that's going to define our g function then. We're going to say g at x, g at x is going to be 2 over, and we want to change the x's, right? So the first thing we want to do is we want to flip it so that what used to be positive is negative. How do we do that? A negative sign. And then we also want to compress it by a factor of 2. We want to compress it by a factor of 2. Now you'd think when you're compressing it by a factor of 2 that you would divide all the x's, right? But what do we know about our x's? They lie to us. So we're actually going to multiply by 2. So we're going to say negative 2x in the bracket. Does that make sense? 2 over negative 2x. Okay, now we said the whole point is if we're changing the y values, then g of x being equal to 2 over, and then in the bracket here, changing it to negative 2x, that should keep all the same y values, right? Because what are we changing here? The x's, right? So what were our y values before? Negative 0.5, negative 1, negative 2, 2, 1, and 0.5. Okay, now listen, look at me here. Before we go here, let's just take a look. We know that what we wanted this to be, right? We want this to be negative 0.5, right? And to get that, what we had to do, I'm going to write real small here, pencils down, okay? Pencils down. But talk to me, I want to get negative 0.5. So I want this to equal negative 0.5, which I got last time by doing 2 over negative 4, right? Do we see that? But I know that now I have to do 2 over negative 2 times something. So what number would I have to put in here so that this bottom ends up equaling negative 4? What number has to go in here? Positive 2. Do we see that? If I put a positive 2 in, positive 2 times negative 2 is negative 4. Can you see that? So, the number I used, not negative. God, it's the worst lesson I've ever taught. Actually, it's the second worst lesson I've ever taught. I'll tell you about the first one later. So, to get the effect that the old x of negative 4 had, what did I actually have to put in? Positive 2. Does that kind of make sense? And again, if it doesn't, that's okay, because we're just going to remember what do our x's do to us? They lie. But let's try another one. What y value do I want to get out here? 1. And last time, how did I do that? I did 2 over, because the function was 2 over x, right? So I did 2 over what? Negative 2. But in our new function, I don't do 2 over x, I do 2 over negative 2 times x. So what x value am I going to put in here if I want that bottom to be negative 2? 1. Good. 2 times negative 2 over negative 2 times 1 is just 2 over negative 2. So the old x value is negative 2. The new x value is just 1. Yeah. Yep. So I could keep going here, but what are we doing to our x values to change it? The function says that we're going to multiply x by negative 2, right? What am I actually doing to change my x values in the new function then? The opposite of that. So the new x values, what I'm going to call x prime, new x value, can be taken by taking the original x value and dividing it by negative 2. Does that make sense?
Is that why there's like that little O there?
Yeah, for original. That works. So what would this x value become? Negative 1 would become negative 1 over negative 2, which is positive a half. Does that make sense? What would 2 become? 2 over negative 2 would become, oh, I did the wrong x value, sorry. What would 1 become? 1 over negative 2 is just negative a half. Or if you like, negative 0.5, that's fine. This could be 0.5. And what about this one? Yeah, we do 2 over negative 2, which is negative 1. And this one would be 4 over negative 2, which is negative 2. And so, I'm going to try to match the colors here. This blue point here, if the x value was negative 4, we're going to go along the same y value, but where is it going to be now? We want it to be flipped. So from negative 4, it will go to positive 4, right? And then we want to compress it down to what? Compress it in half. So we flip it. So negative 4 becomes positive 4. And then we compress it by half. So 4 will become 2. Good. What about this red point? We're going to flip it. So negative 2 will become positive 2. Then we're going to cut it in half, which means that positive 2 will become positive 1. Good. And then this purple point. It was at negative 1. We're going to flip it, so it's going to go to positive 1. Then we're going to cut it in half, so it will be positive 0.5. And so if you look here, we've got half of our function now, and it goes like this. It's been mirrored, but it also, do you see how it's closer to the axis? And then if we deal with the top, we can do the same. This one was at 1. It's going to go to negative 1. Then it's going to get cut in half, so it's going to be negative a half. Right? This one was at 2, so it's going to go to negative 2. And then what's going to happen to it? Cut in half, so it will be negative 1. And this fine fellow here was at positive 4, so it's going to go to negative 4 and then get cut in half and be negative 2. And so when we sketch this side of the graph, and I should use the same, I should have used what they use, red. I'm going to use green, I guess, is a good counterpoint. Oh yeah, so that's g at x.
I tried.
Boy, am I going to erase this video and just teach this again from my living room and post that instead. Jeez Louise. Sorry about that. This isn't quite as bad. The worst lesson I ever taught, I taught a calculus class once and just got so mixed up. This is about, it's about 14 years ago now. But I just got tripped up and made a bunch of mistakes. And finally I looked out and saw so many glazed eyes that I said, all right, everyone stand up. And then I had everyone take the note out of their binder, rip it in half and go throw it in the garbage. And I said, we'll just try again tomorrow. And then I showed like two episodes of The Simpsons. But not today. You guys have got this. Even though I did a terrible job teaching it, you're going to do great with this. Long story short, when we multiply a function, if we multiply it by a big number, we take it and we stretch it up. If we divide it by a number, or multiply it by a decimal, which really means the same thing, instead of stretching it up, we compress it. And if we multiply the whole function by a negative number, we didn't do this yet, but it will go flip, right? If we multiply the y's by negative numbers, instead of going up, they will go down. And then if we act on the x's, it's the same thing, except if we multiply, we would expect the x's to get bigger, but actually the x's get smaller. When we divide, we would expect the x's to get smaller, but actually they get bigger. And if you understand that, you're fine. You understand the whole lesson. Yes, ma'am? Yep. Because if we want to modify the x, we have to change the x, not the function, right? Now, could you factor that 2 out and divide it? Yes. But I don't want to show it that way because I want to show us modifying the x. That would be changing the y's. So that would be like page 1. And the answer is it would make it twice as tall. Which, by the way, would look similar to this because compressing, guys, look here. There's an interesting point, which is that in terms of what the function actually ends up looking like, compressing the x's is the same as stretching the y's, but how it gets there is different. Does that make sense? In one case, you get there by changing all the x's and making them half as big. In another way, you change all the y's by making them twice as tall. Those are going to look the same. And in fact, if you just look at a function, there's no way to know if it was stretched up or compressed in which case my advice to make the math easier is stretch it up, because it's always easier to work outside of the brackets with the y's, because our y's don't lie, and what do our x's do? They lie. So if you see a stretch, you could be like, oh yeah, I could work with the y's or the x's. Always easier to work with the y's. But when it comes to stretches and compressions, you can always do that with the x's or the y's, but reflections can only go one way. In other words, if it used to go up and now it goes down, that has to be a negative sign outside because it changed the outputs. And if it used to go left and now it goes right, that had to change the x's, which means it has to be in. Who's packing up? Sit down. What's up? Yeah, sure. You bet.
Because I lost it at the
That's okay.
so I don't even know.
Okay.